Okay, well, greetings everybody. My name is Dr. Matthew Kidder. I am an economist and I am here to teach you about the consumer choice problem. Ta-da! This is a textbook problem where a consumer is trying to maximize his or her utility. It's a microeconomics problem that you'll see in intermediate and advanced to beginner textbooks, introductory textbooks. It's pretty much like a workhorse. So why am I talking about it today? Well, let's take a look at something. There's a big hole in this literature in terms of education, so I'm trying to fill it. Let's go. Let me show you what I mean, okay? So if I would go consumer choice utility maximization, okay? What I'm going to see here, and this is just Google it. I mean, if you have a hard time with something, always Google. It's great. But what I see here is this graph. This looks very similar to what you'd see in a lot of textbooks. I'm just clicking through Google. You see these kind of indifference curves of budget constraint. Oh, here it is over here. This is the textbook problem that you see. Now, let me just tell you something. They really messed up here when they tried to teach you guys this literature and this stuff, and let me just tell you why. Okay, so what you're looking at here is actually just shadows on a wall. They're showing you literally shadows. Now, okay, that sounds like kind of crazy, Dr. Matt. What's going on, shadows? Well, I'm here to show you what I mean by they're showing you shadows, and I'm here to unveil and unwrap the real thing that is driving this graph and that's driving these shadows so that you can actually see what's going on. So I'm going to present this material in a graphical way. For all you visual learners out there, you're going to love this. Okay, there's going to be other materials that you can look at it in a more mathematical way if you want. This is going to be graphics. So let's take a look at it. What do I mean by shadows on the wall? Well, there's kind of a cool thing with Mathematica. This is a program. This is just a Wolfram Mathematica, and I'm going to make this available on my website, which is mkidder.com. But I just want you to take a look at this drawing over in this portion here and compare it to the textbook scenario here. It looks pretty similar, actually, right? You see that there's, in the textbook scenario, you have a line that makes up a triangle if I consider the origin. That's exactly what I have here. I've got this triangle, which if I ignore the shaded part would just be a budget constraint line. And then I've got these curved kind of indifference curves. So let me just jump to the final result right now. Okay, the final result, if I just rotate this thing, that's what's really going on. Holy wow. What? Okay, I know. That is a lot different, right? Right? So it doesn't shock me that, geez, this stuff gets so confusing to people and they just go about memorizing conditions such as tangency condition, which is where the slope of your budget line is equal to the slope of your indifference curve. That's a tangency condition that everyone memorizes. Why is that the case? Well, I'm here to show it to you graphically. Let's take a look at this. Okay, so this video I'm going to try to segment into two parts. So we've got two objects here. The first part is the utility function, which I want to understand, and I'm going to describe that. And the second part is going to be understanding the budget constraint. And then the third part brings those two things together and helps you understand exactly what utility maximization is. I do want to point one little interesting little tidbit here. If we look, where do we think the tangency condition, if you're familiar with tangency, then great. And if not, then we'll get to it. But if you know it, like where does the tangency look like it occurs here? Look, it's right about in this area. And then if I rotate it, that also happens to be the highest point on my graph. And there's no coincidence about this, folks. It's exactly how it should be by design. So the utility maximization problem, let me just state it very clearly, and then we'll go through it in detail, like I said, is basically it is to get the highest level of utility, which is measured by the height on this colorful curve, but keeping inside of the constraint of your budget, which is everything in the shaded region. So, so that's what we're trying to do. Now let's go understand this step by step. First of all, utility, okay? What we have here are, so let's start off with these indifference curves. And indifference curves, to understand what they are, we need to build in an understanding of what utility actually is. The utility function in these kind of setups is, it's a function of two inputs, two consumer variables. Over here, I just Google, they've got days of skiing. Makes you happy, right? When you go ski. And days of horseback riding. Hey, that makes you happy too. Okay? So, however many days of skiing and days of horseback riding you can have, it's going to make you happier. So, you can think about these bananas and oranges or whatever the case. It doesn't really matter so much. Personally, I think commodities are a little bit easier. So let's go with bananas and oranges. Let's pretend that, now if we look at this thing down in 2 dimensions, okay, we've got, say, bananas on the y-axis, and say oranges on the x-axis, okay? So, and down here we've got quantities, so 10 oranges, 10 bananas, 20, and so on. So, if I take 10 oranges and 10 bananas, it's going to correspond to the point right about here, where these two intersect. And how happy will that make me? That's the question that your utility function answers. How happy that combination makes you is represented as a height, which is on the z-axis. So you get bananas and oranges on the y and x-axis, and those represent a point, which is a combination of the quantities of each of those two. And those two quantities, they correspond to a certain height, which is your utility function. Okay? This is your utility function. This maps out every possible combination of, it maps out every combination of basket of goods and delivers a certain amount of happiness to that basket. Okay? And we can see some nice functions about the utility curve. First of all, there's the assumption that more is always better. So you always say, well, hey, that seems weird. Okay, if I have like 10 bananas, geez, I don't think I want to eat another banana. Why doesn't my happiness start to go down? I mean, eventually I'm going to have bananas coming out of my nose. It's going to be really strange, and I'm not going to like it. So I should be unhappy about having extra bananas at some point, right? Well, actually, so the thing is that that's not quite right, because we're not telling you that you have to eat all the bananas. You can always store them. You can always do something with them, sell them, whatever the case might be. So we assume that more is always better. You don't always have to eat it, but just more is better because you can always do something with this extra stuff, right? But the quality of it is that more, as I give you more, it makes you a little bit less happy than the amount. Let's say I give you one banana when you had none. If you're starving, you're going to be extremely hungry. So the first banana I give you is going to make you super happy. And then, after you've had like 5 bananas, you're like, okay, I'll take another one. But you don't really care too much. And so your utility is going to go up just a little bit more if I give you, as you get more and more bananas, which is called diminishing marginal returns. You see it graphically in this curve by, you see how the slope starts off very steep, which means when I have very few bananas over here, then I get an extra one, it shoots the difference in my utility, it shoots up really high. But you see over here, say I have like 9 bananas, that corresponds to this much utility. If I get one more, it's going to increase, but not as much as it increased in that first one. So that's represented by what they call the concavity of the utility function. So the utility function itself is concave, which if you look at it, it looks kind of like a cave. Like, looks like a little place you could go hide into, right? Little hut. Now the utility itself is concave. Now these indifference curves over here are actually convex. They look like a V. If you were to, like, they're bent in the same way as a V going upwards. So they're not concave like a tent shape. The indifference curves are actually convex, and those are part of the utility. So how do you get convex indifference curves out of clearly concave utility function? Well, now we need to build in the idea of what is an indifference curve. Okay, what are these lines over here? And this is a real key point. Like, what are these lines? So it's very important that you understand what those are. You don't see them here. What they are, so here they are. I put them in 2 dimensions. If I look straight down on this graph, you'll always get the 2-dimensional representation that you see in the textbook, okay? So if I look straight down on this graph, I can see these convex indifference curves on a concave utility function. Well, what these indifference curves are, if I look at them, graphically what they are, let me go up. See if I can get the, oh, it's not going to put those, anyway, I'm just not going to put it right where I want it. So graphically, what these are a certain level of utility. So if I take 10 and I were to just take a slice and slice my utility curve with like a samurai sword right here, just go whack it off at 10, then it would curve, that cut would curve out this line. And what does this line represent again? Remember, if I look down in the 2-dimension space, it represents a basket. So these are all different baskets of oranges and bananas, right? So it represents the different quantities of oranges and bananas that are going to give me the same level of happiness, which I whacked it at 10, right? So it's all in this case, if I take the cut right here on this line at 10, that means all of these combinations of goods are all going to give me a 10 level of utility, okay? And that is exactly what an indifference curve is. Why is it called now it makes sense. Why is it an indifference curve? Well, it's an indifference curve because those are the baskets that you're indifferent about. They give you the same amount of utility. It's the same benefit. So you're like, I don't care if I get, a basket up here or there, because they're going to give me the same amount of like happiness. So I'm indifferent to them, right? That just is all starting to make sense, hopefully now. So these indifference curves, you can see that as we're going out into this region, up, these indifference curves are corresponding to a higher level of utility. So when we move along the curve where we are not, we have the same level of utility along all of these lines. So this line would have the same level, every point on this line has the same level of utility, but as I move up to a line in the upper right direction, we're going to have, this line would be strictly preferred to the one below it. In other words, I'll get higher utility as I move up in this direction. And you can see that, again, it drives another interesting point, that the concavity of utility brings convexity in indifference curves. Wow, spinning around too much. Okay, so that's what utility is, and those are what indifference curves are, and that's why I said that those are literally shadows, because what you're looking at is looking straight down a 2-dimensional graph in your textbook that is really a 3-dimensional object, okay, which they don't tell you about. So here's those indifference curves again. I can rotate it and look straight down at it. I can play with it like this. Rotate it around, you can see how indifference curves work. Okay, and like I said, I'm going to make this this Mathematica notebook available on my website, so you can grab these toys and models and just play with it yourself and see how it works. Now, you see that, again, I made the point, here's the utility with the indifference curves, and what we see in the textbook is we're just projecting those lines down into 2-dimensional space, just looking straight down from the top on it, and that's all we're doing. And so that's component 1 in constrained maximization, which is, the object you're trying to maximize is the utility, okay? You're trying to find the highest point on that curve. Which, if I was going to have it unconstrained, let me just ask you. I was going to say, like, what's the highest amount of utility you can possibly get in this model? Well, it's going to be, you're going to want everything. You're going to say, hey, how about you just give me like infinite bananas and infinite, oranges? Just give it all to me. I mean, not all. Just give me like as many bananas there are as there are grains of sand in this world. Okay, you can just say it like that. But that's kind of contrary to how the world operates, because the central premise of economics is that is one of resource allocation. Okay, so we don't live in a world of just infinite resources where everybody can have infinite. We're constrained, and there's limits to what is actually available, and so those constraints take monetary form in the form of your budget and form of what kind of money you have in your wallet. That's going to determine what is available to you in terms of your purchasing options. And so we modeled that with a budget constraint, which is in the textbook, it's this straight line down here, this budget line. Now, I'll just show you, this is over here, I've written this in terms of x1, which is a good for x1, bananas or apples, whatever. This is the p, x1 is the price of x1, x2 is just another good, and that's the price of that good. So if I look, the budget constraint is defined by this relationship here, which actually should have less than or equal to instead of just less than. But let's just talk about this. What this says is, what is the quantity of x1 times the price of x1? So in other words, like if you went to the store and apples cost like $2, which is the price of apples, and you bought like 3 of them, right? Then so if you bought 3, that's x1, and 2 is the price of an apple. So what is that? Those two things multiplied. What is that? That has real intuitive like thought. That's how much money you spent on apples, right? How much money did you spend? You spent $6 in this case, right? So x1 times p of x1 is how much you spent on this good x1, and again x2 times p x2 is just how much money you spent on x2. Okay, so we're summing these two things together because we're adding these two things. How much did I spend on x1 plus how much did I spend on x2? Okay, we're summing those two things together because we're just assuming that those are the only goods in this economy. And so this is all the money that you've spent. You've spent money on x1 and x2, and that's how much you've spent. And actually, and getting back to it, this should be less than or equal to instead of just less than. And on the right hand side, you have your income. So on the left hand side, you have expenditure, and on the right hand side, you have income. Okay. And you can go ahead and solve that. So then looking at how do you plot this down into 2 dimensions. If this would be, say, quantity of x2, which would be x2 in this case, and this would be like x1 on the x curve, on the x-axis. So you could plot this very simply by just solving your budget constraint equation for x2, which would involve just subtracting this to the right-hand side and then dividing by the whole thing on the right-hand side by px2, and that would give you your equation for this line. Okay. Now, what we're saying here, getting back to some more intuition again, is that why do we have it the case where we're setting it like this? We're actually so why is there a line? Why is there a line in the textbook, and why am I showing you a whole triangle? Remember, I showed you up the very first thing up here. I showed you this whole shaded area. Why did I show you the shaded area? Well, it's because everything inside of that triangle, all the good bundles inside of that triangle are going to be feasible. So I'm just going to take a bigger look at my budget constraint. So here we go. I put this with a little kind of some controls so you can play with it. So in this case, I've got, this is quantity of 30 for x2, this is quantity of 30 for x1. Over here I've got my price of good 1 to be 1, the price of good 2 to be 2, and my income to be 30. So if my income's 30 and these are the prices, price is equal to 1 for both of these things, then what's the maximum that I can possibly buy of x1? Well, that just means I'm going to only spend my money on x1, right? So, and buy nothing of x2. So that means I'm going to spend all of my $30 on x1, which if the price is 1, then that means I can buy 30, which is exactly why the intercept down here is 30. This is the bundle where I get 30 of x1 and 0 of x2, and that corresponds to this point. Now, I could also buy 0 of x2 and 20 of x1. Okay, that's also feasible. Okay, it's feasible. You can do that. You're allowed to do that. But the problem in doing that is that you then generate some waste. Okay, and why is it wasteful? Because first of all, what you're not going to get out of this. So if you don't spend all of your money, then you're going to have some money left over. Okay, and what we've assumed in here is we've assumed fiat currency. Actually, whether you realize it or not, you will see that money itself, income and money, does not directly show up in your utility function. So I've said that in my model, if you just take the model for what it says, I've said you only get utility or happiness out of either x1 or x2. I've said you get 0 utility out of just money in this model. Okay, you can put money into the utility function. That's definitely something you can do. But in the setup here, we're going to say no. You're only going to get utility out of eating these apples or oranges or bananas. So you're not going to get any money out of any happiness out of just having money. Money is just a paper. It's just fiat. It has no utility value. You could care less about who's on the front, so you don't have any artistic value to hang it on your wall. You don't really care to burn it because other things probably burn better. So, it doesn't really serve any direct, purpose for the benefit of your life in this model. So, so that's why you don't save. You're not going to save in this case money or just hoard money because it has no value to you. And we're also working, to make things. I'm not going to go into this, but also you're not looking into the future and worrying about, future types of, there's no kind of what they call precautionary savings or anything like this here. Okay, we're not going to get into that. But here we go. So this is the setup. That's why basically in the textbook example, you only see a line. On the budget line, it says that you're spending all of your money. Remember, the budget line is drawn when I get rid of this inequality up here and I replace that with an equality. When I say this equals, that means your expenditure is equal to your income. It will give you a line, which is right here. So that's the long-winded version, but these are really important things for you to conceptually grasp. So we're trying to get in all the details here. Okay, so let's play with this thing a little bit. What happens when I increase x1 to say 2? Well, how much x1 can I buy? Well, I can buy, if the price is 2, I should be able to buy 15? Yeah, look, it's right down here on the graph. 15 is the maximum bundle I can buy. If I, for x1, it's the most amount of x1 I can possibly buy if I buy 0 of x2. And you'll see if I change the price of x1, then this graph is what they call pivoting. You see, it's just kind of like the intercept for x2 isn't changing at all because I'm not changing the price of x2, but so they call that pivoting around the y-axis when I change the price of x1. And the only two things that are changing when I'm changing the price of x1 are the slope of this line, you'll see as the price is getting higher, that slope is getting steeper, okay? And you can also see that the intercept is changing. Likewise, if I change x2, like this, we're going to pivot around the x1 axis. And as I get higher, we're going to get, the slope is getting flatter, and that's how it works, okay? Now let me ask you a question. If I have, so now if I do income, what happens? Income, I should have done this. Income, what's going to happen here? Okay, if I change my income, it doesn't change the slope of the line. It just expands the axes in and outwards, okay? Let's take this to like 15. Okay, so in this case, if I have 15 income and the price is 1, then this is my utility set. Now what happens if I multiply everything by 2? So what happens if prices of like apples and oranges jump to 2 and my income also jumps to 2? What do you think is going to happen? Give you a chance to think about it. Well, in terms graphically, absolutely nothing. Nothing. If prices all rise, you'll see, look. If prices, say, go up, so your income goes double, but prices go to 2. I should make that. That's close enough. 2 right about there. That's close enough. You'll see that's the exact same constraint. So that makes a point about inflation. When when the price of your wages is keeping up with the price of the inflation of other goods in the economy, then that has no impact on your consumption sets. Your real wealth is not being impacted. When I say real wealth, what I'm talking about is your ability to consume goods. Okay, that's how we want to measure wealth. We don't want to measure things just in dollars. Remember, dollars are useless. That's fiat. We want to measure it in terms of your capacity to consume, your capacity to buy. Okay, now don't get esoteric on me and say, well, we should be more environmentally conscious. Yeah, okay. Shelf that idea for a minute, okay? I understand it's there. But right now, we're talking in a world of just making you personally the happiest. Remember, this is a very self-centered model, okay? This is a very self-centered model representation of the world here because we're only caring about your utility. That's the whole point. So the question now is, we've got budget constraints there. You can consume everything inside of this triangle. So that is going to end our discussion on budget constraints. We've talked about utility, about how about the properties and about what actual level sets are. And now we need to put those two things together. So if I were to look at this problem again in 2 dimensions, you can now see that is a budget constraint. You can consume any bundle in this region, and the question is, which bundle makes you the happiest? Which is the same question as asking which combination of x1 and x2 will give you the highest value on my utility plane, which you see somewhere about in there, right? You can see it kind of visually. Now, if I were to superimpose my level sets and also keep my budget constraint, you see that actually when there's this tangency, basically what that means is with the level set that kind of dives down in here, dives down and just kisses that budget constraint. Just one little peck, one point. It shares only 1 point. That particular level set, okay, is the highest amount of utility that you can possibly get, okay? You can do that, you can think about that visually. What about a level set that doesn't touch it at all? Well, it's not feasible. If it's not touching your budget constraint, that means you can't buy you can't reach that level of utility, right? What about when I say level set, I'm also talking about indifference curves. Those are interchangeable, guys and ladies. So just so we're on the same page here. What about indifference curves that touch your budget set twice, at least? Well, let's look. This one touches it here and also here. So the second one touches my budget constraint twice. It crosses my budget constraint twice, in and out twice. Now, look, you can always see that I could draw a line in between these two, right? That would be upwards and to the right of the line in question, the indifference curve in question. So if this is my indifference curve, this 9.8 here, and it's coming here, I could draw a line, another indifference curve, another level set between these two. Between 9.8 and 11.2, I could draw another indifference curve right in between these two, and that would also be feasible. And remember, that entire indifference curve would be upward and to the right of my original one, which means that it would be a higher level of utility, right? So you can keep on doing this kind of logic until you find one that just touches it just one time. Actually, this one doesn't look like it quite touches, but we're going to pretend that it does, okay, just for convenience sake. The one that just barely touches it one time is and that point actually where it touches it one time is the point that maximizes your utility. That's a result of some calculus. So if you want to go into the calculus, that's constrained optimization, and we're not going to do it here. This is a visual representation. I did this visual representation because when I look through what's out there, it's all shadows. It's all shadows. Look at that. I just Google search it. Let's look at image. Oh, we're on images. There's nothing out there. I can't believe it. I really just feel shocked about some things. I really do. I feel shocked that this is not presented as it really is, and I'm shocked that they just present it as shadows on the wall. So hopefully now it's making like some more sense. I know for me I'm visual, so like I said, there's also mathematical ways to solve this, which we can go over in some detail also. You're going to have tangency condition. The conditions will be the slope of this, your budget constraint is equal to the slope of your indifference curve, and also your second condition will be that it's feasible, which will be your budget constraint. So we can derive those conditions in another exercise, but this is just to complete the visual representation of consumer optimization in 3D. Dr. Matthew Kidder, signing off. Well, actually not signing off. Just joking. Well, now signing off. Bye-bye.